Okay, let's go ahead and get started. So homework 2 is due tonight in just a few hours. Homework 3 is posted. We're going to talk about homework 3 a lot today. But before I do, this is your last chance to ask some questions about homework 2. So does anybody have any questions they need answered about homework 2 stuff before the deadline? Any questions at all? All right. Well, let's talk about homework 3 then. Actually, just a couple quick reminders. There's no class a week from today. 1 week from today, there's no class. I'll be out of town. I'll be at a conference. It's on the calendar, so just be aware of that. And then 2 weeks from today is going to be our first exam, our midterm exam. So we'll have a review session before the exam. But 2 weeks from today is our first exam. If you think that you are unable to make the exam for some reason, please let me know as soon as possible. However, if the reason is because you decided to go on spring break early, I'm not going to be very sympathetic about that. We have class that day. You're expected to be here that day. So if you have a legitimate reason, like there is a university-sanctioned event that you are a part of, get in touch with me so that we can get that sorted out and schedule a make-up exam time. All right, let's talk about homework 3. You can see, actually, first, this is not due for over a month. You have a long time to work on this. There are a couple of reasons for that. One, we got spring break in there, so, I don't know how many of you expect to work on this over spring break. I think it would be a good idea, but I'm also not dumb. I understand that you're probably not going to want to think about this much over spring break. But two, this is not a small lab. This is not a small assignment. So even though it might be tempting to not think about this for a few weeks, do you guys have questions? I hear a lot of talking. Even though it might be tempting to not think about this for a few weeks, I would really highly encourage you to get started on it sooner rather than later for a couple of reasons. One, it's going to take you a while to figure this out. It's not a short assignment. It's not an easy assignment. It's difficult. If you wait until after spring break to start on this, you're going to have about a week left after you get back from spring break to submit this. You can probably do it, but it's not going to be fun. It's not going to be a good time. You're going to be pretty stressed out about it. So please start early. The other reason to start on this early rather than late is that B+ trees are going to be on the exam in 2 weeks. I'm going to ask you about B+ trees on the exam. So this is great practice, great preparation for the upcoming exam. So even though it's not due until after the exam, even though it's not due until after spring break, I still really think it's in your best interest to get started on this now. So the code's in the repository. I'll go over that. Actually, let's just go over that first. There's actually not a ton to go over. I did not provide you with very much starter code at all. I gave you a few simple classes for nodes. So you can see there's an inner node class here with some methods that you'll need to fill out. There is a leaf node class here with some very similar methods that you'll need to fill out. There's a B+ tree class. You can see there's a few methods in here: search, insert, delete, the same stuff we've been talking about in class over the last few days that you'll need to fill out. And that's it. That's really the gist of the assignment, is completing those methods in those classes. Again, though, I don't want to make it sound like it's deceptively simple, because it's not. There's only 3 or 4 methods in each of these files, but they're doing a lot of work, especially the ones in this file, especially the B+ tree itself. It's doing a lot of work, a lot of work. So do not underestimate this assignment. The B+ tree takes in 2 values. What are these values? P inner and P leaf. What are those for? Yeah. They're the degrees of the nodes. So I have an inner node degree and a leaf node degree, right? So this code should be able to handle whatever degrees I throw at it. In fact, if we have time at the end of class today, I want to do a B+ tree example that uses a different set of degrees than what we have been using, because we've only really been using an inner node degree of 3 and a leaf node degree of 2. I want to get out of that and think about what it actually means to use a different degree for our B+ trees. And then it's important to remember, I think, that these are used as an index into a table. So what am I actually storing in a B+ tree? That's what this entry class is for. This is already complete. You don't need to modify it. You can see that it's actually not particularly complicated. It's a key value pair, where the key is a field. That's going to be a value from a table. It could be an int or a string. These trees should also work for strings. These trees should also work for strings. And the value is going to be the page number where I can find that field in the table. So the entries are what's actually being stored in the leaf nodes. These are the actual payload of the tree. There's really not a whole lot to discuss with the code. Let's take a look at a couple of tests and talk about testing this thing. I did supply you with a couple of tests, 2 or 3 tests, I believe, that we can go over very quick. You'll note I think one of the first things you'll notice about these tests is that they're kind of long. I've been preaching about how tests should be, relatively simple and straightforward. These tests are a bit longer than the ones that we're used to on previous assignments, in part just due to the nature of the complexity of the B+ tree that we're working with. And so you can see I do some simple insertions where I just insert 2 values and then make sure those 2 values make it into the root node. I do a more complex insertion where I create the tree and then insert, what is that, like 10 values? This may or may not look familiar to you. It should look familiar to you. This is the exact example that we did in class on the board last week. This is the same exact example that's in the slides that we did on the board last week. And if I scroll down to the deletion test, there's a search test, and then here's a deletion test. It's the same thing. This is the exact deletion example that we did in class on the board. So if you were here that day and you're taking good notes and you followed along the exercise, you have what this should look like, right? You know what this tree should look like. And the test does exactly what you would expect. If I go back up to this insertion test, the first thing that the test does is it inserts a whole bunch of values. Then it starts at the root. I grab the root and I start checking. All right, what should the search key be in the root? From the example that we did in class, I'm not sure I actually remember what it is. Apparently it's a 7. There should be a 7 in the root. All right, let's grab the children of the root. So I'm going to grab, there should be 2 children, right? There should be 2 children. So let's grab those children and check those search keys. So the search keys in the left node apparently are 2 and 4. And then we'll keep going down to the leaf nodes, and I just check all the values the whole way down the tree to make sure the entire tree has the values that I expect. I'm verifying the structure, again, that we had up here on the board when we did this example in class. It should look exactly the same. Exactly the same. And so I want to spend some time today talking about unit tests again. This is sort of a reoccurring theme. We spent some time talking about it last time. You're expected to write some unit tests again. For this assignment. They're due on Monday at noon. You have a few days to do it. So I want to talk a little bit about where some areas might be that could use some testing with this particular assignment. I've given you, like 4 tests, maybe 5. One for simple insert, one for a complex insertion that builds the example from class, one that searches, and then one that does some deletions. But this is not anywhere close to testing everything that this assignment could possibly throw at you. So we've seen some examples of B+ trees. We're somewhat familiar with the structure of B+ trees, right? So my question for you then is, what are some additional things that we should be testing? Does anybody have any thoughts? Yeah, what's up?
How about the results of the insertion if we change our degrees where it's now 3 to 4?
So different degrees should be tested. Now remember, we actually have 2 degrees as part of our tree, right? The internode degree and the leaf node degree. So should we test those at the same time? Should we test those separately? What do we think? The answer is yes. Let's do it both. Let's do a test where we just change the inner, right? Make the inner something different. Do a test where we change the leaf degree, and then do a test where we change both. Make both of them different. And make sure that our tree still looks the way that we would expect it to after changing those values. What else might we consider testing for? It's a tricky question, right? Maybe we can rule out some things that we shouldn't be testing for. Some tests that I saw on the last homework assignment that I actually was not a fan of. I still gave credit because I didn't talk about it too much in class, but I hope I don't see tests like this again. Things like testing getters. No, not necessary. Getters, 1 line of code. I don't need to test that. That's trivial. That's a trivial method to test. I do not want to see tests of getters anymore. From here on out, I will not be giving credit. If you just test a getter, I will not be giving credit for those kinds of tests anymore. So nothing that's trivial, but think about the operations that we're performing. Right now I'm testing insert, delete, and search. But can we get a little bit more detailed about what we're actually testing in those methods? For example, what are some of the things that could happen during an insertion? What are some of the things that I expect could happen during an insertion? I insert a value into the tree. What are the possible options that occur after I insert a value into that tree? Anybody? I see you, ma'am. Can we get somebody else chiming in? Yeah. The tree could be unbalanced. So what needs to happen? Actually, the way we've been inserting values, if we follow the algorithm correctly, should ensure that the tree remains balanced. So I guess what I'm getting at is, what's the algorithm tell us to do? The simplest case if I insert something is what? There's an empty spot in the node. I put it in there. We're done. Right? What's a more complex case? Yeah. The leaf nodes are full. The leaf nodes are full. So I could test some things with insertion, like splitting nodes. That's what happens when I insert something into a node and it's full, right? So I could write a test, a very simple test, that all it does is it tries to set up a tree and then insert a value that's going to force one of those nodes to split, and then check and make sure that the result of that split is what I expect it to be. The insertion test that I gave you kind of already does this, right? But it would be nice to have a much smaller, simpler test that just focuses on this directly without having extra stuff involved. What are some of the other things that could happen during an insertion? So I've got the easy case where I have an empty slot, everything works fine. I've got the more difficult case where I have to split. I mean, maybe we could talk about this in more detail too, right? Where I have to split a leaf node. But then there's the more complex case where after I split the leaf node, what happens? I take a value, push it up the tree, which could cause me to start splitting the inner nodes as well. So let's write a test for that. Write a test that's going to split the inner node. And if I get really into it, right, the inner node could split, which could cause the other node to split, which could cause the other node to split. And ultimately, what's going to happen? I'm going to get to the root. I'm going to have to create a brand new root. That's sort of the extreme case. So create new root is an option that could happen. All right. Let's talk about deletion. So the simplest case of deletion is that I go to the node, I remove it from the node, and what is true? If everything works easily, what's true about the node after I remove the value? If I want to get the best case scenario, what am I hoping for? Yeah. Still more than half full. Still more than half full. So a very simple deletion would have a node that's still more than half full, right? So that's one thing that could happen. What if it's not half full? How can we test what are some of the things that we could test if it's not half full? What are some of the things that the algorithm tells us to do? Yeah. To merge. When does merging happen? When does deletion tell us that we need to perform a merge? Anybody? I'll wait. Yeah. A sibling that has an open spot that we can merge? Kind of. Close. Yeah. An extra value. So that's a different case, actually. Borrowing a value from a sibling is a different... That doesn't actually require a merge. That's just the node gets to stay alive in that case. So borrowing a value is something that we should test for. Value from sibling. Something we should definitely test for, right? When do I merge nodes, though? Yeah. Uh-huh. That's true, but there's another condition as well. It's less than half full and... not empty. It doesn't have to be empty. Less than half full and... Go ahead. One of its siblings is still more than half full. That would mean I could borrow. When do I merge? Yeah. When they're both less than half full, or when all of the siblings, well, all of the siblings can't be less than half full. If I have a node that's less than half full at any time, that's a problem, right? Can't do that. Yeah. I can't borrow. If I get a node that's less than half full, I'm going to try to borrow first. If I can't get a value from one of my siblings, then I merge. So the condition is I try to do this, and that fails, and then I try to do this. All right? Cool? What are some other things that can happen during deletion that we should be testing for? What happens if merging fails? I can't merge because maybe, let me take that back. I successfully merge, but then I have another problem, right? There's not enough nodes to keep my parent alive. Then what happens? Yeah. Deleting a level. So that is one thing that can happen, but we're going to try to do something else first before we delete a level. What are we going to try to do first? We had a term for it. Anybody remember? So I'll put deleting a level on here because that is a thing that can happen. But we're going to try to do something else first. What are we going to try to do first? Yeah. Delete that child. Well, if I just delete that child node, then my tree becomes unbalanced. I have to delete an entire level. I can't just delete part of a level in this tree because then it would become unbalanced. But there's a way that we can keep the inner node alive, right? There's a way that we can keep that inner node alive. There's a technique that we talked about. Yeah. Push through. What's push through again? What do I do if I try to push a value through? I go to the parent. This has to do with inner nodes, right? I'm an inner node at risk of deletion because I'm less than half full. So I go to my parent and I say, hey, I'm about to be deleted unless you can give me a value. Keep me alive. The parent says, okay, hang on a second. I'm going to go to your sibling, see if they have any values. And if they do, it'll grab one of the sibling's values, which actually goes to the parent. And then one of the values that the parent had goes to the node that was in danger of being deleted. That's what we've been calling push through. So the order up here is actually a little mixed up. The first thing that we would try to do is this, borrowing from a sibling. The second thing we would do is then merge nodes. And then merging nodes might have that ripple effect, right? Might cause us to think about the inner nodes, might cause our inner nodes to be less than half full, in which case we would try to do push through first. And if that fails, then that means that we need to get rid of an entire level of the tree. Okay? Yes?
Can you clarify the difference between borrowing from a sibling and pushing through?
Borrowing from a sibling happens on the leaf node level. So I'm just going to steal something from a leaf node, one of my leaf node siblings, to keep a leaf node alive. Push through is purely for inner nodes. The reason that it's different, or maybe somebody can answer this, why isn't push through the same as borrowing? Why doesn't an inner node just go to one of its siblings and say, give me a value? What's stopping it from doing that? What prevents that from happening? Why do I have to bring the parent into things? Yeah. I don't have a linked list for the inner nodes. The leaf nodes have a linked list, or do they, right? Actually, if I look at my inner nodes, you'll notice that I have no such linked list set up here. So if that's something that you want in your implementation, you're going to have to make that happen. I would recommend it. I think it's going to make your life easier if your leaf nodes are put together in a linked list. But ultimately, it's up to you. If you want to skip that, try to do without, that's your decision to make. But in a traditional implementation, my leaf nodes will be linked lists together, so I can see my siblings directly. I can borrow a value from them directly. The inner nodes are not, so I have to go through my parent and ask it for a value. Yeah?
That's the inner node class. I'm using the leaf node class.
Oh, sorry. Yeah. Wrong class. Thank you. Yeah, that's not here either. Nope. Any other questions? So this is a good list. I'm asking you to write 2 unit tests for this assignment. I would really want you to pick, or not really want to, I'm basically telling you to pick your 2 unit tests from this list of stuff. This is the list of options that you have for writing unit tests for this particular assignment. This is what I would like to see. In fact, since we have some time, I'd like to write a unit test for this today, together, in class. But in order to do that, we need to do an example of a B+ tree that has different degrees than what we're used to working with. Because so far, we've been using the same degrees for all of our examples. So let's do an example that uses different degrees. In fact, to make life simple for us, let's do the same example that we did before, but with different degrees on it so that we can see how that's going to affect the tree. And then once we get that example finished, we can write a unit test for that. We'll do it together here in class. So let me pull it up from the website. It's on the slides. Maybe some of you already did this outside of class. If so, you can help me out as I am constructing this B+ tree. Here we go. So we already made this tree with an inner node degree of 3 and a leaf node degree of 2. I want to do this again with an inner node degree of 4 and a leaf node degree of 3. How does increasing the inner node degree change the structure of an inner node? How does changing the degree of an inner node change the structure of that node? Yeah. I'm going to have more children. I'm going to have more children. In fact, the degree of an inner node is the maximum number of children that an inner node can have. So in our previous examples, I could only have 3 children from an inner node. Now I'm saying that we can have 4. What does that mean for the search keys? That's going to go up 2, right? I can now have an additional search key. I need an additional search key. If I have 4 children, I need at least 3 search keys to be able to distinguish between those 4 children. Right? Yes?
Before I find it a bit tricky because, like I would say what the minimum number would need. So would the minimum number be 3 in this case, or could it go down to 2? Because 2 is exactly half, but I think it needs to be like greater than half, so it needs to be 3.
Yeah, that's a good question. When are we considering these nodes to be unacceptable? Is it when we're at exactly half or strictly less than half? And the answer here is actually kind of depends. You know, the implementation can vary depending on how you want to do it. But that is something that we need to decide on and be consistent about. And that's something that we can discuss together as a class because it's going to affect not just how we do this example on the board, but how I write the test and how you implement your B+ tree, right? It's going to have implications on that. So we need to make a decision about that. So let's construct the tree and see what happens. Let's see how we feel about it. I kind of don't want to erase this if I don't have to. Let me see if I can just make room. Okay. Here we go. What's going to happen first? What do I need to start writing up here on the board? What's going to happen first? I'm inserting the 9. So where does it go? In the root. And the root is what kind of node right now? It's a leaf node. It is a leaf node. The root is a leaf node. All right. There's my 9. I insert a 4. So, all right. Now I've got 4 and 9. Now I want to insert a 12. Should I make a new node? No. The degree of our leaf nodes is 3. The degree of a leaf node specifies how many entries it can have. So it's still not full yet. So I can put the 12 in here too. Here's what our tree looks like after inserting the first 3 values. All right, now I want to insert the 7. Now I want to insert the 7. What's going to happen after I insert the 7? Yeah,